Hi, today we are going to study about the successive differentiation. Successive differentiation is nothing. We are going to find the nth order derivative of a given function. A function y is equal to fx which is continuously differentiable, then we will get the nth order derivative. By getting nth order derivative, we can find the any number of derivative. So, the first today we will see about the some different kind of pattern of nth derivative. That's why we can get the another function also. The first function comes out the power function or power series we can also define here. Y is equal to ax plus b to the power, and we write here. Now we will have the nth order derivative. So first we differentiate the function y. This what we get, this will be m a into a and ax plus b to the power m minus 1. As we know the differentiation, again we differentiate second times. What we get, m minus 1 comes out here and one additional a will come out here, so that it will be a square, and this will be ax plus b to the power m minus 2. Now the third times we are differentiating here, it will be m minus 1, m minus 2, and again a will come out here, a cube ax plus b to the power m minus 3. Now we see here the pattern, so that once we put here 2, it will come up to 1, the sequence will come up to 1, a to the power 2, m minus 2 will come here, and once we put here 3, third order derivative we are talking about, m goes to m minus 2, and here a cube ax to the power m minus 3. So now basically what we have the successive differentiation and we have the pattern, so that we directly go to the nth order derivative. So up to, I write here directly n, so that this will goes up to m minus 1, m minus 2, up to m minus n minus 1, and this will be a to the power n ax plus b to the power m minus n. This we have to remember once we go for the nth order derivative of this function. Now we start with the some cases, because we don't know m is an integer, m may be the greater than n, may be the is equals to n, m may be the less than n, m may be the another value. So accordingly we will have the nth order derivative. So I keep this here, and we start with the cases once m will be greater than or less than. So the first condition we have, I write here the case 1. When m is greater than n. M is the power of ax plus b, and n is the number of derivative we require. So basically what we do here now, here we put m is greater than n. As you know, once we have the power is greater than the derivative, for example, if I write here, if you write y is equal to x square, so d2 over dx square, we do not have problem, it will be 2, simple. If we write here 3, then it will be what? 3 into 2 into x. It means once power is greater than the derivative power, so we don't have any problem, we will have the same thing. So once m is greater than n, we will get the same result. There will be no change here, but we have the pattern to derive this. What we do here, yn is equals to m minus 1, m minus 2 up to m minus n minus 1, n plus 1 I write here, and we extend this series up to m minus n, m minus n minus 1, n plus 1 up to 3, 2, 1, and here a to the power n and ax plus b to the power m minus n. Since we have multiplied here, so we have in the denominator start from m minus n, m minus n plus 1 up to 3, 2, 1. Why we are doing this? Because we have to follow one pattern, so that once we put m is equal to different number, we will get the solution. So this will be m factorial, this will be m minus n factorial, a to the power n, ax plus b to the power m minus n. This is your dn y upon dxn. Here we can write dn upon dxn, and your function is ax plus b to the power m. This we get the result. We get this result by putting m is greater than n. Now we have the case 2 when m is equals to n. What happens? Case 2 when m is less than n. It means we require the higher order derivative where the power is less than the derivative. As we know, if you have x square, again I give a simple example. If you have x square and you require d3x square upon dx cube, what we have, it will be 0. Since if 3 is greater than 2. The same thing, if m is greater than n plus 1 and so on, by putting m is equal to n plus 1, n plus 2 and like that, we will have the value 0. Now we come to the case 3 when m is equal to n. See what we do now, we directly put here m is equal to n to get the nth derivative. So dn upon dxn, and your power value is ax plus b to the power n, because we have taken here m is equal to n. What we get? Here we get n factorial. In the denominator we get 0 factorial, a to the power n, and here m is equal to n, so that this will be 0 and the n raised to the power 0 will be 1. So this we get 1. Finally, what we get, it will be n factorial a to the power n. This will be the nth derivative of the given function. Now we have more values. So we have the case 4 when m is equal to minus 1. This is the special case that we introduce here, because once you put m is equal to minus 1, your function will be different from the previous one. By putting case 4 we are talking about, when m is equals to minus 1. In this case, your function y will be ax plus b power minus 1, or it is 1 upon ax plus b. So basically, once we have it is minus 1, we put here m is equals to minus 1, and we get directly the answer. So yn will be minus 1, minus 2, minus 3, minus 1, minus 2, minus 3, up to nth derivative we are talking about, up to n, and this will be a to the power n, ax plus b to the power minus 1 minus n. So it is minus n minus 1. We have not written in the denominator here because we are approaching up to this level only. Here minus 1 minus n we require. So this will be minus 1 to the power n factorial upon a to the power n upon ax plus b to the power n plus 1. Here I repeat again, once we have the nth order derivative, we will go up to this level only. Rest this part we have multiplied here, so we are omitting this time. We will go to up to this minus 1, minus 2, minus 3, minus 4 up to minus n. Up to minus n we are talking about. So by taking minus common, we will have minus 1 to the power n factorial an upon ax plus b to the power n plus 1. This is the standard case in this condition. Now, after having this case 4, we will have again case 5. In this case 5, now we take when y is equals to log ax plus b. This is the next sequence from this. What we get here, first we have the y1. y1 will be what? 1 upon ax plus b, and this a will come out here. So I write here, I write here a here. To go up to the nth order derivative, now we have to differentiate this function up to n minus 1 derivative. So you have the same situation. This is a into this one, ax plus b to the power minus 1. What we have up to nth order derivative, that we put here n minus 1 directly. So what we get, y n is equals to, everywhere we will put n is equals to n minus 1 in here solution. So it will be minus 1 to the power n minus 1. Here it will be n minus 1 factorial. Here this will be a to the power n minus 1, but here a extra we have, so this will be a to the power n, and in the denominator we get ax plus b to the power n. This we get the solution for the nth order derivative. So today we have discussed about the power function or power series we can say. And the 5 cases we have discussed, on the basis of this nth order successive differentiation, we will get any order of derivative of this type of function. This is very useful once we take 1 upon ax plus b. Suppose a function is given in the form of denominator, so using the separation and the partial fraction, we will have the number of nth order derivative. The next is exponential function. Second, exponential function. As we know, the exponential function we can write a x to the power n. So, what we do now, okay. Now we will see about the exponential function. This is y is equals to, the function is a to the power mx. The first derivative we have y1 is equals to what? M a to the power mx log a e. As we know the differentiation of this power exponential function we have. Now y2 will be what? M square a to the power mx and log a base e square. In this successive manner, now we have the successive differentiation procedure we have now. So if you put 2 here, you will get 2 here, you will get 2 here. So directly I write here y to the power nth order derivative. It is m to the power n a mx log a base e power n. This we get the nth order derivative of this given function. By putting a is equals to e, your function will be y e to the power mx. So either we can put directly here a is equals to e, or we can have the successive differentiation also. So if you put a is equals to e, what happens? M to the power n, you will have e to the power mx, and here if you put e log e base e, that will be the one that we know from the logarithm function. So this will be 1. So this will be your answer, dn upon dxn, and your function is e to the power mx, that is m to the power n e to the power mx. This you get the answer. In the next section, we will have some other functions, trigonometrical function, that we will see the successive differentiation, and after that we will have the product function of such kind of these functions. Thank you.